Today we're going to start Chapter 7, and Chapter 7 is titled this really long word called stoichiometry. And in chemistry, stoichiometry is the study of proportions or ratios. It's studying how we're going to mix different chemicals together to get what we want. Kind of like when you're baking, if you get the ratio of like dry ingredients to wet ingredients just right, you get the perfect reaction and your cake has just the right texture. But if you mix them in the wrong ratios, your product may be dry and crumbly and not very good. So for chemistry, it's very similar. This is a concept that we're going to use for the rest of the course. So please try really hard to get a good foundation of stoichiometry. And you'll notice that Chapter 8 is titled More Stoichiometry. It is important that you learn this skill. So when we start learning about stoichiometry, you get introduced to a very new concept called a mole. This is not the little mouse-like creature that you have that digs up your yard, but we use a mole in chemistry as a measurement or a unit for an amount of molecules. Just like we talked about in the last chapter when we had a balanced chemical equation and I would say this means 1 molecule of water. Well, you're not going to be able to sit there and measure out 1 molecule to make a reaction. There's not tweezers small enough that you could sit there and put them together. And so we cannot measure molecules or atoms. They're just too small. So what scientists do is they've made their own measuring unit, and it's called a mole. Just like when you go to the grocery store to buy a bag of rice, you don't buy 1 rice, like 1 piece of rice. You buy a pound or a kilogram. It's too hard to buy rice based on the number of rice grains, and so you buy it by mass. And the same happens when we're talking about atoms. We're going to be measuring out chemicals in your lab with a scale or a balance, and you're measuring them out by mass, not by counting how many molecules there are. And so we get introduced to a concept called a mole. And a mole is a really large number. And so 1 mole has 6.02 times 10 to the 23 atoms or molecules in it. So it would be like if I had 6.02 and then I would have, or 6.202 and I would have 21 decimal or zeros after that. That many atoms makes up a mole. And so you would say, I'm going to take a mole of water, which is 6.02 times 10 to the 23rd, instead of 1 water molecule. This is how we count atoms. Since it's too hard or they're too small to count just 1 atom, we count them in moles. Now, a mole is based upon a hydrogen. Basically, a scientist took 1 gram of hydrogen and did many experiments to determine how many hydrogens are in that 1 gram. And they decided that it is 6.02 times 10 to the 23rd. Now, on your periodic table, we learned a number. And so an example would be on this hydrogen, it's a 1. And for oxygen here, I have a 16. Your periodic table may have it rounded, but we learned this as atomic mass, but this number actually has a second use, and we're actually going to use that more often. And so this number tells me how many grams 1 mole of oxygen weighs. So if I have 6.02 times 10 to the 23rd atoms of oxygen, it weighs 16 grams. And if I have 6.02 times 10 to the 23rd molecules of or atoms of hydrogen, that weighs 1 gram. And so this is how we're going to be measuring out our atoms. And so if you are doing an experiment and you need 1 mole of oxygen, you're going to measure out 16 grams of oxygen. Question number 1 of the comprehension check. If you wanted to collect a mole of magnesium atoms, how much would you collect? So on your periodic table, you're going to be looking for magnesium. And mine says 24.3. And if you're using the periodic table in the front of your book, you actually have more decimal points. So you're going to see that it's 24.31 grams. So if you wanted 1 mole of magnesium, you would take your sample of magnesium and you would mass out 24.31 grams. Question number 2 tells me that if I have 0.5 moles or half a mole of sulfur, how many atoms do I have? So to do this, I'm going to take, it's half a mole, so I'm going to take what 1 mole is and divide it by 2. When you take 6.02 times 10 to the 23rd and you divide it by 2 in your calculator, you need to put parentheses around this entire top number. You're going to have to get used to using parentheses a lot. And this equals 3.01 times 10 to the 23rd. And so that is just half a mole. That's how many atoms are in half of a mole of sulfur. The next question, part of it asks how many grams it is. Now look on your periodic table and you can tell how many grams are in 1 mole of sulfur. 1 mole of sulfur has 32.06 grams, and we only have half of that, so we're going to divide it by 2 to know how much what its mass is. And the mass of half of a mole of sulfur is 16.03 grams. Question 3 is asking how many grams do I need to gather if I want to have 8 moles of water? So if I have my balance, how much water am I going to mass out so that I have exactly 8.1 moles? And you would do this if you were doing a reaction. As we learn later on in this chapter, you will have experiments where you need certain amount of moles or certain amount of molecules of compounds. And so you'll have to be able to mass them out. Now, I cannot tell you the mass of 8.1 moles unless I can tell you the mass of 1 mole of water. So to calculate the mass of 1 mole of water, we're going to get introduced to a term called molar mass. The molar mass is the amount of grams it takes to make a mole. So it's like how many grams 1 mole of water makes. And so we're going to calculate it for water. So to calculate a molar mass, you're going to take each of the components and add them together. For water, we have 2 hydrogens, and if you look on your periodic table, a mole of each hydrogen is 1.01 grams. So I have 2 of those. And then I also have 1 oxygen, which is 16 grams. When I add this all up, I get 18.02, and the unit on this is grams per mole. So this is how many grams 1 mole of water makes. And I got this by adding up the molar mass of hydrogen, the mass of another hydrogen, plus that of oxygen, straight from your periodic table. So if I know that 1 mole weighs 18.02 grams, I can calculate how much is going to be in 8.10 moles. Now I'm going to set these up in the method called the factor label method that you may remember from calculating units. And it is important that you set them up this way, even though it may feel a little simple at first, but these problems are going to get very long and they're going to end up having sometimes 5 to 6 steps to them. And so it is important that you learn how to show your work and show your steps so that you don't get lost in the longer problems. So I'm going to write what I'm starting with, which is 8.10 moles. And it's very important to keep your units as you're doing this. Now I'm going to use this molar mass, which is a ratio of grams to moles, to convert from moles to grams. I want moles to cancel out, so I'm going to put it on the bottom. And so I'm going to use the conversion factor 8.02 grams per mole. And moles is going to cancel out, and I'm going to be left with an answer in grams. When you do the multiplication, you get 146 grams of water. So what that means, if I took a sample of 146 grams of water, in that would be 8.1 moles of water. Now we're going to report our answer with 3 significant figures because in the data that I put in, I have 3 significant figures. So the next part of the question is asking me how many molecules that I have. So to calculate how many molecules I have, down here, I'm going to write this problem in the same method that I wrote the first step. The reason I'm doing that is I want you to get very familiar with what this looks like. So I'm starting with 8.10 moles. And if I'm going from moles to molecules, I'm going to be using this number here of 6.02 times 10 to the 23rd. It's called Avogadro's number after the scientist who developed it. Now, there can be 6.02 times 10 to the 23rd molecules in a mole, or it also could be atoms in a mole. That unit can change between molecules and atoms. But since water is a molecule, not an atom, I'm going to use molecules. So I have moles on the top, and it's going to cancel out with moles on the bottom. And you're going to put this multiplication in your calculator and get in the habit of using parentheses. When you put this math in your calculator, you should get 4.88 times 10 to the 24th molecules of water. And remember to keep with your 3 significant figures. Question number 4 has us using the same ratio, just in a different way. It says that we have 309 grams of NH3, and that's ammonia, and it wants us to know how many moles that is. Well, the last problem they gave us moles and we went to grams, but this time we're doing the opposite. So since we're using grams and moles, we're going to use that molar mass conversion factor that goes between grams and moles. And we're going to have to calculate the molar mass of NH3. So you're going to look for nitrogen on your periodic table and see what its mass is. Nitrogen on your periodic table has a mass of 14.01. So you're going to add 14.01, and then we have 3 hydrogens, and each hydrogen has a molar mass of 1.01. So I have that 3 times. When you add all those up, you get your ratio that we're going to use for this of 17.04 grams per mole. Now, our problem gives us 309 grams, so that's what I have to start with. I'm going from grams to moles, so I'm going to put for this conversion factor what I'm going to on top. Sometimes I write mole and leave the E out. And I'm going to put grams on the bottom. That way the grams will cancel out. And so in order to do this, I have to put the 17.04 on the bottom. So you're basically taking this ratio and you're flipping it. We flip it so that grams will cancel out and we're going to be left with our answer in moles. Now when you put this in your calculator, you're going to put in 309 and you're going to put divided by 17.04. Your answer is going to be 18.1 moles of NH3. And you have 3 significant figures, so you're going to have 3 significant figures in your answer. So what we just figured out is if I have 309 grams of ammonia, sitting in that 309 grams of ammonia is 18.1 moles of NH3. Number 5 is long and a bit confusing, but we're going to make sense of it. So I'm going to start off with reading the problem. So we have a sample of sodium carbonate, and it has a hydrated form and an anhydrous form. If you just read that a hydrated form is a compound that has water in it, and an anhydrous form does not. Now, a compound that is hydrated with water is not actually always going to be a liquid. It can still be a powder or a solid, but there's just some H2O molecules bound up in the compound. You can sometimes heat those and you can push out the extra water, and there's an experiment that you may do where you do that. So you have a sample that has no water or it can have water in it. And it tells me that if I have 14.2 grams of this sodium carbonate, it can absorb 24 grams of water. So if you have 14.2 grams of this dry powder that is anhydrous with no water in it, you could actually add into that compound 24 grams of water. So the question says, how many water molecules can be absorbed by each sodium carbonate? And so one of the things that I tell my kids when you start stoichiometry problems, if you are looking at these problems and you're like, I have no idea what I should do, you should always convert to moles as your first step. Even if you don't really know why, you're probably going to get some partial credit for converting to moles. But the reason we convert to moles is when we're dealing with stoichiometry and the ratios of chemical reactions, we aren't usually dealing with the ratio of mass. We'll say is 1 mole of this substance reacts with 2 moles of another. So since we deal with ratios in moles, always convert to moles first. So the first one I'm going to convert to moles is the sodium carbonate, and so it's 14.2 grams. To figure out how to go from grams to moles, you need your molar mass, which you're going to get by adding up all the parts of the compound from your periodic table. To figure out the molar mass of this compound, you're going to add up 2 sodiums, and each one is 22.99. Then you're going to add in 1 carbon, which is 12.01, and all these numbers are coming from your periodic table, and 3 oxygens, which each is 16. Make sure and double check this math. Put in your calculator twice. It's not that hard to do, but it drives me crazy when a student makes a very simple addition mistake because they didn't want to do it twice to make sure they got the same answer twice. Once I have my molar mass or my ratio, I can easily convert from grams to moles. I go from grams to moles, I have to flip the ratio. I have to do the thing where I kind of flip the ratio. That way the grams that I'm starting with will cancel out with the grams in the ratio. So I have to put grams on the bottom. So when you put this in your calculator, you're going to set it up as 14.2 divided by 105.99. You should get 0.314 moles of Na2CO3. So now we know how many moles we have of this. I need to figure out how many moles it reacts with of water. Now I don't have moles of water, I have grams of water. So once again, I'm going to convert from grams to moles. To convert from grams to moles, I need to know the molar mass of water. So I'm going to take two hydrogens, which is 1.01 and 1.01, and I'm going to add it to the mass of oxygen, which is 16, and you get the molar mass of water. You should end up with 18.02 grams per mole. We'll actually use this one a lot, so you may memorize it. Since I have 24 grams of water and I'm going to moles, I'm going to take my conversion unit and flip it again and put grams on the bottom. That way grams cancels out and I'm left with my unit in moles. And so you're going to do this division in your calculator. You should get 1.33 moles of water. So now that I know how many moles of sodium carbonate react with moles of water, I can make my formula. So when you do something with a hydrate, they're going to put a little dot in the middle, and you may be tempted to take these ratios and put it in front and say something like 0.314 moles reacts with 1.33 moles of water, which is not incorrect, except if you remember from balancing chemical equations that we cannot put decimals here. These have to be whole number ratios. And so I have to figure out a whole number ratio that these are reacting in. And I'm going to do that by making a ratio myself to see if I can simplify them. So I'm going to set the water over the Na2CO3. So the water is 1.33 moles, and this one is 0.314. So like I said, this is a hard problem, so if you're really kind of confused at this, it's okay. But I'm just trying to compare so I can get these numbers to simple whole number ratios. And so if I compare the water to the Na2CO3, and I'm comparing moles because I'm dealing with stoichiometry and I'm working in moles, I would have 1.33 divided by 0.314. If you put that in your calculator, you get 9.93, which is basically 10. We don't round much in this class, but we are going to round here, 9.93 to 10. And so if this becomes a 10, what I know is that I have 10 water molecules for every one of this. So there's a 1 here, and you would have a 10 here. A 1 Na2CO3 or sodium carbonate can have 10 water molecules to it. For question number 6, you're going to learn about how moles are used in the chemical equation. And so in our chemical equation where we have these coefficients, in the last chapter I referred to them as atoms or molecules, but what these are is we can also look at these as moles, and we can use these as ratios. So we can say 2 moles of aluminum will go to produce 2 moles of aluminum bromide. And I hope you recognize this is a formation reaction. And they give you this reaction already balanced, but it's a good habit to go ahead and check before. And the problem gives you one more bit of information to go with this formation reaction. And the one bit of information it gives you is it says that we have 0.407 moles of aluminum bromide. They're telling me I want to make 0.407 moles of aluminum bromide. So how many moles do I have to start with? I only have one bit of information that they gave me in the problem, and so I have to start with that information. To go from moles of one part of the chemical equation, we can use the coefficients as whole number ratios to convert to other parts of the problem. So I'm going to give you an example. That's the best way to do this. Since I'm going to moles of aluminum, because I'm wanting to know how much of each of these, I'm going to put moles of aluminum top, and I'm going to put moles of aluminum bromide on the bottom. That way they cancel out. And if you'll notice, I'm being very careful and making sure I write down all my units. Now, the numbers that go here are my coefficients from my balanced chemical equation. So I can see that 2 moles of aluminum make 2 moles of aluminum bromide. Simplified, this is just a 1-to-1 ratio, but I do want to walk you through all the steps so that you can see how we get it. You don't actually have to do any math in your calculator. I guess if you wanted to, you could say 0.407 times 2 divided by 2, but 2 over 2 becomes 1. So it's just 0.407 times 1. And so I know that to produce this much aluminum bromide, I have to start with this much of aluminum. So the other part of the problem is calculating how many moles of bromide I have. So I'm going to start with the number that they gave me in the problem, which is 0.407 moles of aluminum bromide, and I'm going to convert it to moles of bromide to figure out what I have to start with. And I'm going to do that by putting aluminum bromide on the bottom. That way my units cancel out. And the numbers that go in front of this comes from my balanced periodic table. So I have 3 of bromide and 2 here. So now you're going to go ahead and put this in your calculator. You can do this by saying 0.407 times 3 divided by 2. And you should get 0.611 moles of Br2. So what this means is that if you took 0.407 moles of aluminum and you reacted it with 0.661 moles of Br2, you would get 0.407 moles of AlBr3. Before we get to question 7, I'm going to use this one to help explain. So this would react, this is like a perfect ratio. If I was to react these two reactants to produce this product, I would consume all of my reactants up and I wouldn't have anything extra laying around. Just kind of like sometimes when you're in the kitchen cooking or baking, if you're baking a cake, you may have a dozen eggs in your refrigerator, but you don't use the whole dozen. You only use 2 or 3 of the eggs and you have some leftovers. Also, what can happen when you're in the kitchen baking is you may only have 2 eggs and you want to make more cake, but you can't because you don't have enough eggs. Those eggs are limiting how much cake you can make. So that is called our limiting reactant. So a lot of times in chemistry, you're not going to mix things in perfect ratios. There's always going to be one thing that limits how far the reaction goes, and that's what gets run out of first. If it's your eggs or if it is your aluminum, it's whatever component you run out of first. Then you're also going to have another reactant that's called the excess, and that reactant you usually have too much of. And that is going to be your cheaper reactant. That is frequently water, right? We always have plenty of water in the kitchen. In America, I'm not really worried about running out of water. Parts of the world, that's a different situation. But the reactant that you can run out of first is going to be usually your more expensive reactant. And because you don't want to waste any of it, you want to use it all up. And it's what limits how much product you make. Question 7 is a little hard to understand unless you do the experiment. It's a pretty easy one to do. But it says in your experiment where you have acetic acid and baking soda in your bottles, it wants you to tell which reactant's in excess in this bottle and which reactant is in excess in this bottle. So what this experiment is you have 3 water bottles, and in each water bottle you're going to add 50 milliliters of vinegar, so the vinegar never changes. And then in the first one you add 2 grams of baking soda, the next one 4 grams of baking soda, and then 6 grams of baking soda. And you actually put the baking soda in the balloon, put the balloon on the bottle, and then you shake the baking soda into the bottle. And what happens is this is your basic volcano experiment, but it's going to produce a lot of carbon dioxide gas and it gets caught in the balloon. You can see how much gas is produced by making a guesstimate about balloon sizes. And so in the first one, it's wanting me to try to predict what is the excess and what is the excess in this reaction and what is the excess in this reaction. In this reaction, I only have 2 grams of baking soda and I have 50 milliliters of vinegar. Now, if I keep the same amount of vinegar and I add more baking soda to it, more reaction happens because more bubbles form and it gets bigger. So what is happening here is baking soda is limiting this reaction and vinegar is in excess. Because if I added more baking soda, there's more vinegar to react. Now the middle one is actually reacting what we call stoichiometric proportion, so it is in the appropriate proportions to react in. The last one, when you have more baking soda to vinegar. So the balloons should be the same size. So as I add more baking soda, the balloon does not get bigger. The reason this happens is you can keep adding more baking soda and it is not going to produce more gas because you've run out of vinegar for the reaction. So what is in excess here is the baking soda.